So what are the characteristics of a Hermitian operator? Why are we interested in it? First of all, we're going to postulate that Hermitian operators represent, give us a way to extract values of properties for the system. And those properties must be real numbers, okay? So the nice thing about Hermitian operators is they have real eigenvalues. So that means we can postulate that the values that we can get if we make measurements are eigenvalues of a Hermitian operator. Okay, so we don't want our theory to give us complex number for something that's real. Okay. We don't want it to give us a complex number that has an imaginary component. Real number. I understand. Real numbers are complex numbers, a subset of complex numbers. Yes, you're right. But what I meant was, you want to make sure that your eigenvalues are real. Okay, so if like I said, if you have a complex number, okay, when can it be real? When can z be equal to z star? Well, what is z star? A minus bi. So z is equal to z star if the imaginary component is 0. So in other words, you have a real number. Okay? All right. Now, we're also going to talk about Hermitian operators having a complete orthonormal set. We're going to go through that in the next few slides. And then sometime later, we're going to talk about Hermitian operators, okay, consequences of Hermitian operators commuting and not commuting. And we're going to get to that later. Okay, so for now, let's just look at the fact that Hermitian operators have real eigenvalues. Okay? So here's the proof that Hermitian operators have real eigenvalues. So let's say f is an eigenfunction of A, operator A, okay? And the eigenvalue is A. What does this mean? If I were to write A hat f, what do I get? I get back the original function, the eigenfunction f, and then I get multiplied by the eigenvalue, which is a constant, right? That's what that means. So what happens if A is Hermitian? Well, let's examine what happens if you take this integral right here. Integral of f star A hat f d tau, which I'm writing here in bracket notation. Okay? Since A is Hermitian, that means I can switch f and f, okay, and put a star outside, right? So this is a definition of Hermitian operator. And so if that's the case, what did I do here? I look at the left side here, A hat operating on F. I just took out that thing right there, so I just combined them. Okay? And what is this? Same thing we showed before. This thing is the same thing as this, right? Get rid of that one. So if I have F, A hat, F star, that's the same thing as if I were to put the A. This is true that if I do this, I can say F, A hat, F star. And remember, if I switch these two now, I just get one. A hat, F, F, star, star. And star, star cancels out, right? So now that's really that. You can actually think of that as another way of defining a Hermitian operator. So both of these are really definitions of Hermitian operator. Okay? So if that's the case, what happens to the left side? F, what's A hat applied on F? It gives you a little a times F, where A is the eigenvalue, right? But what is A hat applied on F? Also little a times F. Okay, so let's write this in standard integral form. Integral of F star, let's do this one on the left, little a, okay, times the F d tau. What do we have on the right side? Oh, yeah. And what do we have on the right side? Integral of AF. Since AF is in the broad, the whole thing, AF has a star. It's complex conjugate, right? So this right here must have a star. Okay? Times F, measure F, d tau. Okay? So, what can we do now? A is a constant. What can you do to a constant in an integral? You can pull it out of the integral. So A F star F d tau must be equal to, what is AF star? That's just A star F star. But A star is also just another constant, so I can also pull that out of the integral, right? So I can say A star integral of F star F d tau. Okay? So A must be equal to A star. Unless F is 0 everywhere, in which case that integral is 0. In general, then A is going to be equal to A star. And we're not interested in functions that are 0 everywhere anyway. Okay? So A is equal to A star, therefore A is